10.4 Lesson 3, Polar Coordinates and Polar Graphs. Our objectives for today are 1. You'll be able to find slopes of tangent lines to polar curves. 2. You'll be able to find points of horizontal and vertical tangency to a polar curve. And 3. You'll be able to find tangent lines at the pole for graphs of polar equations. And we have our vocabulary that we went over in earlier lessons. And of course, we're also discussing about tangent lines today. So for the first objective, suppose we have a polar equation r is equal to f of theta. The graph will be a curve in the polar plane, and the question is, how can we find the slope of a tangent line to a point on our curve? Before we answer the question, we should make an important distinction between dr d theta, the derivative of r with respect to theta, versus dy dx. And when we're asking how can we find the slope of a tangent line to a point on our curve, we want to find dy dx, not dr d theta. What information will dr d theta give us? Let's go ahead and make our discussion concrete by looking at a specific polar equation, and we will find dr d theta and discuss what information is given by dr d theta, and then we will talk about how we can find dy dx for a given polar equation. Dr d theta is very easy to find. You just differentiate this polar equation with respect to theta. So you have the constant 5 multiplied by cosine of theta, and so you will have negative 5 sine theta. But the important thing for us is to understand the significance of dr d theta. It is the rate of change of r with respect to theta. And in polar coordinates, we have r theta, and we know that r is telling us the directed distance of a point on our curve from the pole, and theta is the directed angle from the polar axis. So this is saying how fast is a point on the polar curve either moving away from the pole or moving towards the pole for each unit of change in theta. So the kind of information you can get from dr d theta is whether you have a point on the polar curve moving towards the pole or away from the pole at a particular point on the curve, as the curve is being traced as theta values are increasing. That's different from what we want to know in this particular part of the lesson, which is the slope of a tangent line to a point on our curve, which is instead given by dy dx. So how can we find dy dx for a polar equation? The answer is we're going to rewrite our polar equation in parametric form first, and then use the parametric form of the derivative to find dy dx. To rewrite our polar equation in parametric form, we will use our coordinate conversion equations. So we will have x is equal to r times cosine theta. This is our given polar equation telling us what r is. So we will have 5 times cosine theta. So that's r. And then we have to multiply that by cosine theta. And then for y, we will have r times sine theta. So r is 5 times cosine theta. And then we have to multiply that by sine theta, as we have here in our coordinate conversion equations. Now we have a set of parametric equations, and we can find dy dx for a set of parametric equations by using Theorem 10.7, the parametric form of the derivative, which we can find by doing dy dt divided by dx dt. Or in our case, dy d theta divided by dx d theta. That would give us dy dx. Continuing with our example, here's our polar equation we rewrote it as a set of parametric equations, and we can use the parametric form of the derivative to find dy dx by finding dy d theta and then dividing by dx d theta. Now, to find dy d theta, you will recognize that your parametric equation for y is a product of two differentiable functions, so you need to use the product rule in either form. They're equivalent. The second form is directly from the proof of the product rule, but the first form may be easier to remember and extend to products of more than two functions. So we can use either form, and let's go ahead and use, for example, the second form to find dy d theta. So to find dy d theta, we use the product rule. So it is the first function times the derivative of the second. So we will have 5 times cosine theta multiplied by the derivative of sine theta, which would be cosine theta, plus the second function, which is sine theta, multiplied by the derivative of the first function. The derivative of 5 times cosine theta is negative 5 times sine theta. So we will have minus 5 times sine squared theta. So that is dy d theta. Of course, we can write the numerator cosine theta times cosine theta as cosine squared theta. And that's what we have for dy d theta. And in the denominator, we have dx d theta. So notice that the parametric equation for x is a product of two functions, or you can write it also as 5 times cosine squared theta. So x can also be written as 5 times cosine squared theta. And if you want to find the derivative of x with respect to theta from the way I wrote it here, you can use the chain rule. So let's do that, and we will have first, you will notice that the outside function is raising to the second power, and the inside function is the cosine function. There is also a constant multiple of 5. So you're going to use the power rule first. The derivative of the outside function, use the power rule. So 5 times 2 is 10, and you will have 10 times cosine to the first power of theta. And then the chain rule says multiply by the derivative of the inside function. So we multiply by the derivative of cosine, which is negative sine, and this gives us our derivative. Normally we like to write sine first. It doesn't really matter. And there it is. That's our dy dx. Of course, you could simplify by factoring out a 5 from the numerator. And then in the denominator, you have negative 10 sine theta times cosine theta. And you can cancel the common factor of 5, leaving you with negative 1/2 times cosine squared theta minus sine squared theta. You can simplify even further using trig identities. There is a double angle formula that tells us that cosine squared theta minus sine squared theta is cosine of 2 theta. So that will give you minus cosine of 2 theta in the numerator. And in the denominator, you have 2 times sine theta times cosine theta. And there is a double angle formula that tells us that that's equal to sine of 2 theta. So, of course, cosine over sine is cotangent. So our final simplification would be negative cotangent of 2 theta. And that's going to be our dy dx. And that will tell us the slopes of tangent lines to particular points on our polar curve. So we just looked at an example for objective 1. You'll be able to find slopes of tangent lines to polar curves. We found dy dx for a given polar equation by first rewriting it as a set of parametric equations and then using the parametric form of the derivative. And then once you have that, you can use that to find slopes of tangent lines to the polar curve at various points on the polar curve. You would find the value of theta that would give you a particular point on the polar curve, and then evaluate dy dx at that value of theta to find the slope of the tangent line to the polar curve at a particular point. Before we look at objective 2, and to do objective 2, you need to use the results from objective 1. Objective 2 is to find points of horizontal and vertical tangency to a polar curve. We'd like to spend just a little bit more time with objective 1. We did this for a specific polar equation. We took the polar equation r is equal to 5 times cosine theta, and we found dy dx for that. But you can actually generalize the process that we followed to come up with a formula or a theorem that would give you the same result, which would allow you to find slopes of tangent lines to polar curves. Of course, you don't really need this theorem if you were to follow the process that you just saw with my example, but if you generalize that process, you get a theorem that would tell you slopes of tangent lines to polar curves. So let's look at that. We're just going to do, in general, what we did for our specific example. So again, make sure you understand that we're finding dy dx, not dr d theta. Suppose we have a polar equation r is equal to f of theta. The graph will be a curve in the polar plane. How can we find the slope of a tangent line to a point on our curve? So we need to find dy dx. So with our specific example, we began by writing our polar equation as a set of parametric equations using the coordinate conversion equations. So we're going to do that in general. So using our coordinate conversion equations, we may write that our polar equation may be represented as x is equal to r times cosine theta. R is given by f of theta, so we will substitute f of theta for r. Multiply that by cosine theta, and y is equal to r times sine theta. You will remember from our specific example that once we wrote our polar equation as a set of parametric equations, we were able to find dy dx by using the parametric form of the derivative. So we found dy d theta and divide that by dx d theta. So we're going to do the same thing, but for our generic set of parametric equations representing a polar curve. And just like we did before, we need to use the product rule. So to find dy d theta, we will recognize that y is a product of f of theta and sine theta, and we will find the derivative of the product by using the product rule. So we will have the derivative, the first function, which would be f of theta, times the derivative of the second function, the derivative of sine is cosine, plus the second function, which would be sine, and we multiply that by the derivative of the first function, which would be f prime of theta. All of that divided by dx d theta, and we can find dx d theta by using the product rule. The first function would be f of theta times the derivative of the second. The derivative of cosine is negative sine, plus the second function, which would be cosine, multiplied by the derivative of the first. And of course here you can certainly switch the order of the factors and write f prime of theta first. So you'll have f prime of theta times sine theta, and in the denominator you can do the same. You can switch the order of the factors and write f prime of theta first. And this is the theorem stated in your textbook as Theorem 10.11, and that gives you the slope in polar form. So if you're given a polar equation r is equal to f of theta, this will tell you the slope of a tangent line to a point on your polar curve. If you know the corresponding theta value and f of theta, which is of course the r value. But of course, you don't really need to memorize this because you can go through this process each time, as you saw with our initial example. This is more useful for the next theorem that we will look at. Slope in polar form, Theorem 10.11, will be used when we look at the derivation of the theorem for finding tangent lines at the pole for graphs of polar equations. But we'll get to that in a little bit. So now we'd like to look at Objective 2. You'll be able to find points of horizontal and vertical tangency to a polar curve. Let's revisit the problem that we began with, which is r is equal to 5 times cosine theta. And we'd like to go ahead and use this problem to help us with our objective, finding points of horizontal and vertical tangency to our polar curve. You can graph this polar equation, and this is the graph that you will see. You can see that I sketched this graph using Desmos. What you need to do is you need to first go to the wrench symbol, and you will have the option of switching from rectangular to polar coordinates. So you can click on the icon for the polar coordinates, and then you can enter your polar equation as r is equal to a function of theta, and you can specify the range of values for theta, and you will get this circle for the graph of r is equal to 5 times cosine theta. It is a circle oriented as you see, and this 5 is in fact the diameter of our circle. We found that dy dx is equal to cosine of 2 theta over negative sine of 2 theta. The negative sign from dy dx is coming from dx d theta. And we can use dy dx to help us with our objective, which is to find points of horizontal and vertical tangency to our polar curve. When you look at the graph of our polar equation, we of course have a circle, and there are 2 points of horizontal tangency. There's one here, where the tangent line is horizontal with a slope of 0. There's one at the bottom of the circle, and then there are 2 points of vertical tangency, one on the right side of the circle, where the tangent line is the slope of the tangent line is undefined, and one on the left side of the circle, where the slope of the tangent line is undefined. So to find where the graph will have horizontal tangent lines, you can look at dy dx, and you can see that when dy dx is equal to 0, you'll have tangent lines whose slopes are 0. In other words, the 2 horizontal tangent lines. And for dy dx to be equal to 0, the numerator must be equal to 0, while the denominator cannot be equal to 0. And then to find where you have vertical tangent lines, you can set dy dx, you can consider dy dx. For the slopes of the tangent lines to be undefined, the denominator has to be 0, while the numerator cannot be 0. So that's how you find points of horizontal and vertical tangency to a polar curve. So let's go through the process. So we begin by finding our points of horizontal tangency. We can begin by setting dy d theta equal to 0 and solving for the angle. So we want to solve for the angle 2 theta. That would make cosine equal to 0. Remember that cosine of an angle of revolution is equal to the x-coordinate of the corresponding point on the circle. So the angles that would make cosine equal to 0 are pi over 2 and 3 pi over 2. So we can write the angle 2 theta, which is our angle or the argument in our equation, has to be 2 pi plus pi times n, where n is an integer. So now you can solve for theta. So you have multiply both sides of this equation by 1/2, and you get theta would be equal to pi over 4 plus pi over 2n, where n is an integer. So if n is 0, you get theta is equal to pi over 4. If n is 1, you get theta is equal to pi over 4 plus pi over 2, which would be 3 pi over 4. If n is equal to 2, you get pi over 4 plus pi, which is going to be 5 pi over 4. If n is equal to 3, and you'll have additional values. But one thing to note is that our circle is traced on the interval from theta is equal to 0 to pi. So just restricting ourselves to the interval from 0 to pi is sufficient, because the whole circle would be traced when theta goes from 0 to pi. So we can stop after getting to 3 pi over 4. But observe that the instructions actually state find points of horizontal tangency to the polar curve. So we now know that we will have the potential to have horizontal tangent lines at these two values of theta. You also want to make sure that the denominator of dy dx will not be equal to 0 at the same values of theta, and it will not be for this problem. So what we have is the following. We have that we will have horizontal tangent lines to our polar curve at the points that correspond to these two values of theta. So to find the points of horizontal tangency, we need to go back to our polar equation, and we need to evaluate our polar equation at theta is equal to pi over 4 and at theta is equal to 3 pi over 4. So we will have r is equal to 5 times cosine of pi over 4. We know cosine of pi over 4 is square root of 2 over 2. So one point of horizontal tangency would be right here, and the angle would be pi over 4. And the point that we have would be, so we have the coordinates of the point in polar coordinates are theta. The angle of rotation is pi over 4 radians, and r would be 5 square root of 2 over 2. And at this point, we have a horizontal tangent line to our polar curve. And the other point at which we have a horizontal tangent line to our polar curve would happen at theta is equal to 3 pi over 4. Now, here's the terminal side of the angle 3 pi over 4. So r would have to be a negative value to get a point on the opposite ray. This is the opposite ray from our angle, and this is the other point at which we have a horizontal tangent line to our curve. The coordinates of that point in polar coordinates would be r theta, where theta would be 3 pi over 4. And what would r be? You can go back to the polar equation that we began with. R is equal to 5 times cosine of theta, and evaluate that at theta is equal to 3 pi over 4, and you'll have 5 times cosine of 3 pi over 4. Cosine of 3 pi over 4 is negative square root of 2 over 2. So you get r is equal to negative 5 over 2 times the square root of 2. So that's the other point at which our polar curve will have a horizontal tangent line. Find points of horizontal and vertical tangency to our polar curve. So we have found our points of horizontal tangency, and we express the coordinates of our points in polar coordinates. So how do you find points of vertical tangency? You begin by setting dx d theta equal to 0. So we have negative sine of 2 theta. Set that equal to 0, and you need to solve for the angles 2 theta that would make negative sine of 2 theta equal to 0. You can multiply both sides of the equation by negative 1, which will give you sine of 2 theta is equal to 0. You're still looking for the angles 2 theta that would make sine equal to 0. Remember that we use the unit circle to define sine of an angle to be the y-coordinate of the corresponding point. So the angles where the y-coordinates are 0 would be either 0 or pi, and we will have 2 theta is equal to pi n, where n is an integer. And if n is 0, you'll have pi times 0, which is 0. If n is 1, you'll have pi times 1, which is pi. But of course, this is for the argument 2 theta, but we want to identify theta, so we need to multiply both sides of this equation by 1/2. So we have pi over 2n, where n is an integer. And we need to go ahead and start listing the angles between 0 and pi, at which dy dx would be undefined. So now that we have this, we can just go ahead and substitute values of n, where n is an integer, into pi over 2 times n. So if n is 0, then we'll have 0 for our angle. If n is 1, we'll have pi over 2 for our angle. And if n is 2, we will have pi for our angle. But we don't really need pi, because it will just give us the same point on our circle as when theta is equal to 0. So we just really need the first 2, and that would give us the 2 points on our circle where we have vertical tangent lines. Of course, you also want to verify that at these 2 values of theta, dy d theta is not equal to 0, but in this case that will not be the case. So now the last step is just like we saw with finding points of horizontal tangency. We need to find coordinates in polar coordinates for the points at which we have our vertical tangent lines. So to do that, you just take the values of theta that you found and substitute for theta in our polar equation. So we have our first point of vertical tangency when theta is equal to 0 and r is equal to 5. And of course, here's the angle theta is equal to 0. And this is the point 5 units on the terminal side of the angle, 5 units from the pole. So here we have our vertical tangent line. And the question is, find points of vertical tangency to the polar curve. And we found that point of vertical tangency. And the other point at which we have a vertical tangent line would be when theta is equal to pi over 2. So we have r is equal to 5 times cosine of theta. Cosine of pi over 2 is 0. So you have 5 times 0 is 0. And that would be the point right here, having coordinates 0 for r and pi over 2 for theta, and there is a vertical tangent line to our curve at that point. Now you can see that for the other point, the coordinates would be r is 5 and theta would be 0. So we have found points of horizontal and vertical tangency to our polar curve. We would like to conclude by looking at Objective 3. You'll be able to find tangent lines at the pole for graphs of polar equations. So we just worked with Theorem 10.11, slope in polar form. If f is a differentiable function of theta, then the slope of the tangent line to the graph of our polar equation r is equal to f of theta at the point r theta in polar coordinates is given by dy dx. And of course we get this from the parametric form of the derivative, and here's the formula. Provided that dx d theta is not equal to 0 at the point r theta in polar coordinates. Our third objective is you'll be able to find tangent lines at the pole for graphs of polar equations. And the key word here is at the pole. And the coordinates of any point at the pole, you would have 0 for r, and theta could be any value. It really doesn't matter. But if r is 0, you'll have a point at the pole. And this is how we're going to begin our approach to thinking about you'll be able to find tangent lines at the pole for graphs of polar equations. So we begin with our polar equation, r is equal to f of theta, and we're going to designate our angle by using the Greek letter alpha. So we have an angle alpha, and we will suppose that f of alpha is equal to 0. And what is f of alpha? It's telling us what r is. And we're making r equal to 0 because we're considering a point at the pole where r is equal to 0. We would also like to suppose that f prime of alpha is not equal to 0, and the reason for that will become apparent when you look at what we're about to do next. Remember what our objective is. You'll be able to find tangent lines at the pole for graphs of polar equations. So we want to begin by finding slopes of the tangent lines at the pole. When you have a point on a polar curve passing through the pole, how do you find the slope of the tangent line to the polar curve at such a point? Well, you can begin with the slope in polar form, because this is what you use to find the slopes of tangent lines to polar curves at points on the curve. So based on our assumptions that we have a point at the pole and that f prime of alpha is not equal to 0, we can make substitutions into our theorem that gives us slope in polar form. So let's go ahead and see what happens when we find dy dx. So we will have dy dx. Now we're supposing that when we have the angle such that we will have a point at the pole, we're supposing that r is equal to 0, or f of alpha is equal to 0. So we can replace f of... So basically what we're doing is we're taking our result from Theorem 10.11 and we're evaluating that at theta is equal to alpha, where alpha is the angle that would give us a point at the pole on our curve. So when we do that, we have the following. So f of alpha is 0 times cosine theta, and I'm just getting this from our slope in polar form theorem, plus f prime of alpha, which we know to be not equal to 0 by our assumption, times sine of theta, divided by negative f of alpha. Now f of alpha is 0 by our assumption that we have a point at the pole, times sine of theta, plus f prime of alpha, which is not equal to 0 by our assumption, times cosine of theta. So what does this simplify to? 0 times cosine of theta is 0. 0 times sine of theta is 0. So this simplifies to f prime of alpha times sine theta divided by f prime of alpha times cosine theta. And furthermore, because we're assuming that f prime of theta is not equal to 0, and we have the same factor in the numerator and the denominator, we can cancel the non-zero common factors and get just sine of theta over cosine theta. So dy dx would simplify to sine theta over cosine theta, or simply tangent of theta, when you have a point on your polar curve at the pole. I would like to make one correction. I said earlier that we're evaluating our slope in polar form theorem when theta is equal to alpha, so I should have written alpha wherever I saw theta. So I should have had alpha here, and I should have also had alpha here and here. So all of this should be alpha. So what does this tell us? It tells us how to find slopes of tangent lines at the pole for graphs of polar equations. The slopes of tangent lines at the pole for graphs of polar equations will be given by tangent of alpha, where alpha is the angle that gives you a point at the pole. And you can see that this result is derived from Theorem 10.1, slope in polar form. And that result is stated as Theorem 10.12, tangent lines at the pole. If f of alpha is equal to 0, in other words, the r value in your polar coordinates is equal to 0, which means you have a point at the pole, and f prime of alpha is not equal to 0, and the reason why we need that, you can see that from the derivation that we did, that we canceled the non-zero common factor of f prime of alpha to simplify our result. And the result that we have is the following. This is our result. Then the line theta is equal to alpha is tangent at the pole to the graph of our polar equation. And of course, this result, then the line theta is equal to alpha is tangent at the pole to the graph of our polar equation, is from what we just saw in our derivation, that dy dx at theta is equal to alpha, which gives you a point at the pole, is equal to tangent of alpha. And you may remember that tangent of theta is equal to y over x. This is a conversion equation between polar and rectangular coordinate systems. And you can write y is equal to tangent of theta times x. So whatever this is, it is in fact the slope of the tangent line. I will give you an example to help you understand that. So consider the polar equation theta is equal to 5 pi over 6. Now we know tangent of 5 pi over 6 will be equal to y over x. From this conversion equation, tangent of 5 pi over 6 is negative 1 over square root of 3. And if you solve this equation for y, you get y is equal to negative 1 over square root of 3 times x, or if you rationalize the denominator, negative square root of 3 over 3x. So the point that I want to make is tangent of 5 pi over 6 is this value, which is the slope of our tangent line. And when you graph this rectangular equation, you will get the same graph as when you graph this polar equation. They will give you the same line. So to simplify our results, we can just say, well, we know from the derivation of Theorem 10.12 that the slope of the tangent line will be tangent of alpha, and when you take that slope of the tangent line and write a rectangular equation and graph it, you get the same tangent line as if you were to graph the polar equation theta is equal to alpha, as demonstrated by our example with a particular value for alpha. So basically, this leads to the conclusion, which is really simple. The conclusion is really simple. If you have a point at the pole, let me read that again. If you have a point at the pole and the derivative of your polar equation with respect to theta, dr d theta, this is dr d theta, at theta is equal to alpha is not equal to 0, then the conclusion is really simple. The line theta is equal to alpha, the angle that gives you the point at the pole, is tangent at the pole to the graph of the polar equation. So suppose we have this example, and the instructions are as follows. Find the tangent lines at the pole. So the first thing that we have to do is we have to find the values of theta that would give us points at the pole. And remember, when does that happen? That happens when r is equal to 0. So what we need to do is we need to set f of theta equal to 0, and we will have 2 times cosine of 3 theta, and we need to solve this equation for theta. Divide both sides of the equation by 2. So we have the equation cosine of 3 theta is equal to 0. So remember, cosine of theta is x, and we see that x is equal to 0 at these two angles. But in our equation, the angle is represented by 3 theta. So we need to write 3 theta is equal to pi over 2 plus pi n, where n is an integer. So you can solve for theta by multiplying both sides of the equation by 1/3. So when you do that, you get pi over 6 plus pi over 3n, where n is an integer. And then you're going to list the angles on a particular interval for theta, and the graph of this polar equation is a rose curve. And the 3 petals of the rose curve would be traced on the interval from theta is equal to 0 to theta is equal to pi. So you only need to list the angles between 0 and pi that will give you points at the pole. So when n is equal to 0, you just have pi over 6. When n is equal to 1, you have pi over 6 plus pi over 3. And that will be pi over 2. And when n is equal to 2, you have pi over 6 plus 2 pi over 3, and that's going to be 5 pi over 6. So when you have the instructions, find the tangent lines at the pole, you need to first find the values of theta that will give you points at the pole for your polar curve. And these are the values of theta that will give us points at the pole. And once you have that, it's really easy using Theorem 10.12. If you have a point at the pole and the derivative of your polar equation at those values, pi over 6, pi over 2, and 5 pi over 6 is not equal to 0, then the line theta is equal to alpha is tangent at the pole to the graph of the polar equation. You should verify that dr d theta is not equal to 0 at these angles, and you can find dr d theta and evaluate it at each of these angles to make sure that it's not equal to 0. It's not equal to 0 in our problem. So now the conclusion of the theorem is simply this. The line theta is equal to alpha, this is a polar equation, theta is equal to alpha, is tangent at the pole to the graph of the polar equation. So we will have three tangent lines at the pole. The first tangent line will be theta is equal to pi over 6, which is a polar equation. The second one would be theta is equal to pi over 2, which is a polar equation. And the third one will be theta is equal to 5 pi over 6, which is also a polar equation. So here you see the graph of our polar equation on the interval from 0 to pi. It is a rose curve. And as we saw earlier from our work, we see that there are three tangent lines at the pole. The first tangent line is the line theta is equal to pi over 6, and here's the angle pi over 6, so you have this line. The second one is theta is equal to pi over 2, here's the angle pi over 2, and you have this tangent line. And the third one is theta is equal to 5 pi over 6, here's the angle 5 pi over 6, and you have this particular tangent line. So the way you will see that happening is if you use Desmos and you sketch this polar equation and you add a slider and you let the value for the slider go from 0 to pi, you will see that you approach the pole from different directions. And as you're approaching the pole like this, the first tangent line you'll have is pi over 6. Theta is equal to pi over 6. And then you continue and look at the mark that I'm showing you with now green. And then the second tangent line is the one that you have here when you approach the pole as I've shown you. And this is the second tangent line that you get. And so on. And I believe you'll get the third one like this. You can verify, and maybe I made a mistake for one or two of them, but that's the idea. You have three different tangent lines because you're approaching the pole from different directions, even though it's all the same point. So we just looked at objective 3. You'll be able to find tangent lines at the pole for graphs of polar equations.